Hello and welcome to Uncle Data, and I'm collaborating with PyCon Lithuania this year to bring you podcast conversations with keynote speakers. And today I'm joined by Brandon Rhodes, and we're going to talk about his journey in the Python community, his astronomy-related open source projects like PyEphem and Skyfield, and what it takes to teach and speak about Python at conferences all around the world. So who's not familiar with Brandon, he's probably best known for the astronomy libraries I mentioned, and as well as his talks through all out the world, and he was also, I think, a chair of PyCon US somewhere 2016, 2017. And for more of the Pythonistas, you can also know him from Pandas from the ground up tutorial, which he helped, I guess, tons of people to get started with Pandas in general. So, Brandon, I know we're catching before your keynote tomorrow. How are you feeling about it? Is all slides and confidence at this point ready, or are you doing some few tweaks to it?
The slides are in surprisingly good shape. Hopefully we'll get sleep tonight, despite the difference in time zones. And I plan to be quite coherent tomorrow. I will say the slides have stayed sort of in flux, in a change, a little longer than some other talks that I've written. Some talks are driven by a particular idea I quickly want to share. There's something technical I've seen that annoys me and that I want to correct or argue against. And those talks tend to turn into slides pretty easily, and the slides retain a fixed form. In this case, the ideas I'm trying to explore are a little bigger, a little vaguer, and so I'm on the third version of the slide deck. Twice in the last couple of weeks, kind of torn it up and reformed it, and I'm really starting to like the direction it takes. It's often only the third or fourth time through a practice that I realize that I go off on topics that aren't really related to the point I'm trying to make. And I'll look at the time on the timer when I finish a little practice run through, and I'll realize that it would be better to trim out the things that I think are fascinating side topics that really need to be out of the way so that I can make it to the main point. But to do that, I have to discover the main point. And I think that I now have discovered the main point of this talk, and we'll be ready to go tomorrow.
Nice. I'm extremely excited to actually hear what you're gonna share from your, and the more interesting part, what did you cut out, which is the most exciting part for you, right? So one of the things is actually, what I wanted to know, what sparked your interest in astronomy, and actually those two libraries, like open source libraries in general.
My interest in astronomy, I think, goes back to childhood, to having my father or my grandfather point out to me Jupiter, the Big Dipper, Orion standing tall in the winter sky when it's cold out. My grandfather had an old Unix computer back in the early 90s, an early Unix desktop, and he was able to get off of an FTP server, maybe. He was retired but had access to Georgia Tech's computer systems and got an old program called PyEphem, short for ephemeris, table of astronomy positions. And he could run it, and we could sit and we could watch it run. Floating point was so slow back then that you could see it fill the screen as it told you when the sun would rise and set, and the moon and Jupiter. And it could draw a little diagram on your screen of where the planets were in the solar system. And I was fascinated at the idea that you could draw our solar system using characters on a screen. So when I got to university and discovered the Python programming language, I immediately conceived of hooking it up to that old ephemeris program that was still online, still on an FTP site, and I got permission. That was before the days of wide open source licensing. I got permission from the man who wrote it to include the core astronomy computation in a little Python library that I could distribute. So that was the very first offering that I made to the Python community, is I uploaded something that would let you print the coordinates of Jupiter or of the sun or moon to your screen. And of course, then when you were in Python, you could do a loop of your own to find when they rose, when they set, when Jupiter was better placed for observing with your telescope, and what time of the year it wasn't visible. There are all kinds of problems you can solve if you can just get those numbers generated in a Python script. And so that library, which is still up and working, went through several versions. And after living with it for a while, I realized it had a terrible API. The things that we did in the 90s were just appalling. And so my more recent astronomy library, Skyfield, was a chance to reimagine a more Pythonic way of asking for planet and satellite coordinates.
Okay. So for me, the most interesting part actually is, that like for me who didn't do or like wasn't fascinated or did a deep dive in astronomy, is like those complex movements actually of, orbital mechanics, and the physics behind it. How does that even translate, to something like how the calculations even look like?
The old FM library, and so PyEphem that wraps it up, used a set of solutions that were developed last century using, if I recall, a lot of sine and cosine series to model the way that over time each planet's orbit expands, contracts, precesses, adjusts as it's operated on by the orbits and positions of all the other planets. So Saturn and Jupiter, both having extensive mass, influence each other and tug at each other and modify each other's orbits in ways that are semi-periodic, and at moderate precision can be modeled as semi-periodic expansions, contractions, and adjustments. So for any given date, you figure out what the parameters of its orbit are, and then you use a well-known routine originally implemented by Kepler to figure out exactly its position on that orbit at the given date. We now know that at high precision, there is no real periodicity. Orbits are chaos, are chaos math that run forward without ever repeating an element or a position. And so these days, NASA simply runs very big simulations of a few thousand years of how the orbits of the whole solar system play out. And then it's kind of boring. They store that in a big table. You go into the table and you read off where Jupiter is today from their table. None of it happens on your own computer, which is very disappointing for people. There are still objects like the smaller asteroids, like satellites we put into orbit around our own planet, where we still do modeling of an orbit, where NASA didn't bother to include every single little asteroid and no Earth satellites in their huge models. So that still happens on your own processor, that you load up the recent coordinates for the International Space Station, and a little routine on your computer uses your CPU to try to figure out, to try to guess how the moon and the planets will have tweaked its orbit over the last few hours and give you a position. So it varies with the object how the position is generated.
Okay, so that sounds like fun. Like you have some things that you're calculating, and some of the part already abstracted, basically by the calculations, like you mentioned in NASA. So one of the questions, since my personal experience is working with data. So how do you, adjust or integrate the ever-changing things on NASA side, or they don't do any changes, that are breaking backwards?
That was an interesting API decision, given that NASA comes out with new, the big tables are called an ephemeris, and so several of them are called ephemerides, I believe, in Latin. We can also call them ephemerises if we want. They periodically come out with new ones, and I decided to leave it explicitly up to the user which one they would load. And this is different from the patterns I used when I was younger. Somehow, when I was younger, I thought that the the best APIs were the ones that hit all of the details and that had brilliant default settings and could guess exactly what you needed and wanted. And I feel like back in the 20-aughts, I feel like there was this sort of competition. You wanted the top of your web page to have some example code. Here's how you produce the position of Jupiter. You wanted it to be 2 lines. And one of those was an import statement. I feel like web frameworks in the 20-aughts were all competing to show you how few lines you could write and have a working hello world web page. And with some aspects of my new Skyfield library, I did get caught up in that. There are a few bits of configuration it chooses by default. But the ephemeris was something that even in the early versions of Skyfield, I didn't feel I should choose on behalf of the user. The ephemeris I usually use is, I think, 15 megabytes. Some of them are gigabytes in size. Some of them work for 100 years, 200 years to either side of the present, and some try to extrapolate for thousands of years for people who might be reading ancient Assyrian tablets and trying to correlate them with the positions of astronomical bodies. And that's not a decision I should make for the user. And so after 1 or 2 experiments where I did try putting one NASA ephemeris on PyPI as a Python package, I declared bankruptcy, got out of that business, and then made another API mistake. I did include a little download library in Skyfield because I didn't want my example to have too many lines of code. I didn't want to suggest that you had to install some third-party library like requests or something if you wanted to get an ephemeris off of the... I now wish that I had just, in that first example, said, hey, you go get the ephemeris. Here's some example code that'll get it with requests. Here's some example code that'll get it with the Python standard library. But you're going to do it yourself. Instead, I wanted a simpler example. I wanted simpler example code. And so I wound up with a little download library that now I've needed to maintain, and I need to answer questions about SSL certs on Windows. And anyway, so I did indulge in some I.O. that, looking back, maybe I should not have, but I didn't try to make the choice for the user. The examples all use the simple little 15 megabyte DE, the ephemeris that I tend to use. And then I have a whole little page in the docs that explains the more modern ephemerides, their size, the years that they cover, their accuracy, and I let the user make that decision. That way, it appears explicitly in their code. I find that if the example code they cut and paste has an extra line or two, that actually doesn't matter. They're just going to cut and paste it and be thrilled that it works. And if it has the name of an ephemeris in it, then it is explicit in their code from that first cut and paste from my website that a decision's being made right here. And you can run with that default and never change it if you don't care to. But write in your code, if the question ever comes up, you'll be able to see the choice that was made rather than trying to dig into a default that's hidden in the documentation.
Ooh, okay, that's interesting. And yeah, like in regards to making your code shorter, or more simpler for users to read, usually comes to the a bit worse user experience, I guess. And I guess I have a follow-up question to this is maybe when you're talking to your users or getting the feedback about your libraries, maybe you encountered some some interesting usage of your libraries. You mentioned that people might go back a couple thousand years back to match the ancient civilizations. Maybe some other kind of usages you heard.
So first, I should mention that my project is very distinct from what professional astronomers do. They have a large project that they have sometimes Google Summer of Code. They have grad students and professional astronomers working on it called AstroPy. And AstroPy has all the things professionals do. How to measure the spectrum from a star and try to find the hydrogen lines in it. How to get a blurry image and try to process it to get as much information about the galaxy that it depicts as possible. My astronomy libraries, they print numbers. They tell you where things are in the sky. They are more what an observatory manager would need to know than a day-to-day work of a professional astronomer. Astronomers spend most of their time on the data that they've collected, and relatively a small amount of time pointing a telescope or planning an observation and telling someone else how to point a large and expensive telescope. So what can you do with coordinates? You can plan observations. When is something going to be visible and in the middle of the night sky? You can point a telescope. You can draw pretty pictures. If you can generate the positions of thousands of stars, you can make a diagram of the constellations and show where a planet or a galaxy or an Earth satellite will be as it crosses the sky. Two usages that or I'd say three usages that come up repeatedly. There are people in cultures that still use the stars to predict things or govern their calendars, and they sometimes ask questions. There are people that love creating their own almanac. I mean, you can go and order a book called an almanac that tells you where the stars and planets will be, and sailors used to use them on the high seas. And there are several hobbyists that build their own almanacs, say, for their own exact location on Earth. And they will often be the ones that file issues about, say, my rising and setting routines. A normal user will ask about sunrise or sunset a few times. Someone producing an almanac for all year for all locations on Earth asks about a lot of sunrises and sunsets and will come up with an edge case where a particular location in Norway where the sun barely grazes the horizon this one day of the year puts my rising and setting routines in a difficult spot where maybe they detect the rising but not the setting because it's such a slight angle against the horizon. And so that's a class of users that really exercise the library across a lot of different data points. But I'll say that the real majority use is for Earth satellites in orbit. And I had not anticipated when I added that feature that would become the main use case. I often don't get to know the story behind every question that I'm asked and every issue that's opened. And I don't want to pry because I know that some of them are at private corporations or perhaps governments. But I note that they not only sometimes ask questions about how to get a current data on a satellite and determine where it is in the sky, not only ask questions about tracking it minute to minute if they want an antenna aimed at it, not only ask about how to plan groups of satellite orbits. They want to build new satellite orbits that will have features that their client or that their boss is asking for. But there are people that are looking down from a satellite and wanting to do the math of which area of the Earth is covered by the satellite's, say, its camera system from moment to moment, given its orientation as it passes overhead. And the emergence of CubeSats and the number of satellites being put up really has brought Earth satellite positions to the forefront in a way that I don't think they were even last decade.
Interesting. I didn't even thought about these kind of usages because, like, actually it can be used, in many different ways. From like checking your crops, in some cases, right? If there are some patches or like fires or whatnot, as well, from the surveillance and like espionage or whatnot.
I was told when I went to Georgia Tech, I remember a professor talking about, I believe he had worked at the time, it was classified secret, on some of our very first satellites. And everyone thought that our very first satellites with sophisticated cameras were all simply trying to monitor military bases, missile launch sites, research sites. But he said that a number of the early ones, or the ones that he worked on, were infrared. Because as our military planners had thought about World War III, what could cause it? What could trigger it? How could it be avoided? One of the top causes they could think of, once their analysts had looked at the Soviet economy, was that one of their 2 fertilizer factories might burn down. They didn't have a lot of redundancy, and if half of their fertilizer was production was suddenly gone, it wasn't clear that they would be able to feed their people the next winter, and that an invasion of Western Europe might have been undertaken simply because starvation was the likely result, or that some sort of, or that other scenarios could have played out where they would have needed to capture either fertilizer or that productive capacity elsewhere. And so we had satellites looking down and measuring the heat radiated, absorbed from the Soviet Union's grain fields. And given the amount of corruption within the Soviet system, it was believed that we had a far better picture month to month of Soviet agricultural production than they themselves had. And we watched that carefully, and we nursed that carefully, and we knew that a lot of the food that we sent as friends of the Third World overseas, in fact, wound up in Russia. And we wanted that because we didn't want Russia to get hungry enough to burn the world down.
Okay, now that took an interesting turn. So let's move, to more of Python topics, in general. So you're an author of one amazing book, which I didn't read. I'm gonna be honest, right? About the, I think it's network programming.
Yes,
do we call it
network
correct?
programming.
So how did that idea came to you, and how did it all ended up as a book?
In that case, I had been going to Python conferences for a little while and was contacted by a publisher. They had, maybe back in the 20-aughts, published a book on Python network programming, and its advice was now looking out of date. Now that Python 2 was fairly mature, Python 3, I think, was already starting to be on the horizon, and they were looking for someone who could take that first edition of the book and update it for modern practices. So I said yes, and I took on the project because I had some familiarity from having done some with networking in grad school. I knew how sockets worked. I knew how the web worked in detail, and I could jump in and try to update it, both to show how use of Python was improving from where it had been in the 20-aughts, and also to replace the library recommendations with more modern ones. I think that requests might have just come out, for example. So all the things in the book about the web didn't have to use HTTP-lib. And so it was a lot of work, I found, adjusting chapters that someone else had written, because this wasn't scoped to be a big project, but I kept wanting to rewrite things to sort of tell the story of each feature, of each kind of networking protocol in my own way. And so anyway, that the book came out, had some chapters I tried to leave alone, and some became extensively revised. And then I did do another smaller project to update for Python 3 a few years later, and come out with appropriately the third edition of the book, which put parens around every single print statement.
Print statements. I guess that's
Sorry, print. function built in.
But that's that's how all of the people are usually getting into the Python, right? Print world, right? Or let's do print instead of logging. So from that end, my question comes in like, so how do you see the learners? How did they change throughout the years and throughout of your different editions of your book? Did you have to adapt some specific things? Because just like the generation who's reading the book tends to learn differently.
I feel like the Python So it feels like there is a mismatch between, in one sense, sort of the purpose of the book and Python as a language, in the sense that Python is very accessible. It's an easy way to get started, and its standard library is renowned for just providing raw access to the Unix API. Other languages, given, say, a socket, decide that they need to write their own socket class, which has everything spelled their way and has methods with camel case that they've come up with. And so when you sit down to use their socket class, you often find two things. One, you don't know the name of anything because they've given nice object-oriented names to all of the operations that a socket can perform. So you're having to constantly mapping between what you know about Unix sockets and the system calls and trying to figure out what they're called in this object-oriented interface. And second, you have the problem that maybe the object-oriented interface, and trying to be convenient, isn't letting you get at all the details even if you need to. And thank goodness, whatever early person wrote the socket module for Python just put a thin wrapper. I think they just turned all the socket system calls into methods that thus passed in the file descriptor for you, but otherwise left send and recv and everything completely unchanged. You could transfer all of your Unix knowledge over from how you use sockets in C to how you use sockets in Python. And I feel that early generations of Python coders were often coming from a background of C or a scripting language and moving over already knowing Unix, already knowing how it works, how things were spelled, and were prepared to do low-level things using those mechanisms. I feel like each edition of the book included higher and higher level libraries. People weren't using sockets as much anymore. They wanted to, of course, everyone wants to talk on the web. That request library seems to be the main thing people want to do. But also, as the editions of the book went along, message queues like 0MQ appeared, which the book uses as an example. Message queues were huge in the 20-teens, so they got a nice big chapter. And also things like Paramiko to be able to speak SSH natively. That got a big chapter. But I found that as time went on, those details started to become more and more rare in Python code because the era of people SSHing to a bunch of servers to configure them was very much of the early 20-teens. That was huge to be able to use Fabric or something else to SSH everywhere and get everything set up. With the arrival of containers, with the arrival of whole systems to corral your containers, set them up, tear them down. We're not really SSHing from Python anymore to get lots of servers set up, or not most of us. So I feel that the problems that were being solved by scripts in the early 20-teens have now disappeared into large orchestration systems for containers. The cloud has arrived. And so I feel like a lot of the chapters in the book are kind of orphaned, have become more boutique, shall I say. And the real gorilla left standing is, of course, requests. Everyone still needs to do web requests, but not everyone needs to SSH into 100 servers in a for loop.
Yeah, that's fair. That's fair. So I guess, since I'm, coming from, like I mentioned, from the data. For me, is the interesting part is, and which I know a bit more is like your tutorial pandas from the ground up, right? How did that idea came to you?
I needed it, and so I wrote it. So a lot of my projects derive from the fact that if I can figure something out and explain it to myself, then I can turn around and explain it to other people. There are some people who can operate at a very high level of abstraction. They can have conversations at a very vague and high level of abstraction. I've seen, like administrators at work and directors just have these, they have these very vague conversations. And at the end, they've apparently made a decision and are content. And I have no idea what's been decided because I'm very concrete. I'm not abstract. And with something like pandas, I really enjoyed my first experiences with it. I figured out one or two maneuvers, but then I couldn't figure out how to go back the other way. I would get into these situations where I would unstack for a moment to be able to do a summary or a grouping, and then I would not be able to figure out how to stack again and get it back in the form I wanted. I essentially conceived of pandas as these different maneuvers you could make, this kind of graph of maneuvers that would take you to different states, and I only knew a few of those, but then I couldn't come back and get my data back into shape at the end. And so I just sat down and I started sort of learning. And all right, if I'm going to stack, how do I get back to where I was? Because I had a data frame and I did my last unstacking and now it's like a series and it doesn't look like a data frame anymore and I don't know how to go the other way. And so I I read examples, and one of my big problems with example code, especially early documentation for things like NumPy and pandas, would say, ooh, watch what this does. Let's create a 4x4 grid of random numbers. And now we'll compute its variance. And look, it's more random numbers. And I would have no idea what had just been accomplished because I wouldn't have a good sense for what the variance of some random numbers I'd never seen before should be. And so I chose for that tutorial a data set. Movies and actors. Because that's a data set where if I do a join, how many movies has George Clooney been in? I kind of have a sense that that should be in the dozens. If I get back thousands of rows, probably done something wrong. 3 rows. I've probably overly limited my my query. So actors in movies, I kind of have a sense for the size and the shape of that data set. And so if I do a summary, I understand what the numbers mean. And so I chose a data set that was meaningful and where I had a lot of context and where I hoped an audience would have a lot of context. And then I went through each pandas operation forwards and then just did a couple of hours of work to figure out how to go back the other way, drew a kind of little map for myself of where I could go with a data frame, simplifying it or then combining things again, and then starting simple and building, wrote exercises that tried to get people to try sorting out by itself, try grouping out by itself. Now see if you can sort and group. Well, what if you group and then sort? And tried to just take people combinatorially through the possibilities by just asking for one slightly more complicated thing than they had just done, to lead them through pandas abilities in an order that then helped me understand what the possibilities were once I had a data frame in a given shape. Because I do find pandas code difficult to read later. With a Python list or dictionary, I can often keep up in my head with what it looks like. Unless I add comments to my pandas code, once I'm several stacks, unstacks, groups, and sorts in, I'm not sure what it looks like anymore, and I either have to add little comments partway through, by now this is what it looks like, or I have to add print statements when going back through the code later to remember what it looks like after, say, 6 operations.
Mm. Okay, that actually now when you mention your flow and everything, it kind of makes sense, like because usually what tutorials are doing wrong is that they're trying to explain very, very like complex things to people who are kind of new to the topic in general in a very, very complex way. So they just go in, they just run the snippet of code, they get something like you mentioned, random numbers and then random numbers. And they, okay, it works, but you don't understand the context, you don't understand the ideas. And like, I guess one of the biggest like reasons why our tutorial is a good way for everyone to start if they don't, it's just because, you break it down in a very simple and iterative way for them to actually get to know how it works.
Yes, that's very well described. There's a sort of idea that's applied in a lot of different contexts of holding things constant and maybe trying to change one thing at a time. So there are stories about startups that decide to use an exciting new language they've heard about and an exciting new data store and an exciting new programming paradigm because everything should be new. And they don't necessarily create the cleanest code or the best design of their lives. And so you'll see blog posts saying, well, how about you change one thing? Like try a new language, but keep your data store, your methodology, your servers the same this time so that you can just keep doing what you were doing there. If you're going to try the cloud and going to try Kubernetes, maybe keep using your old language and change one thing at a time. And so with the idea of learning pandas through a familiar data set, my idea was let's not change everything on you at once. Let's get a data set that you know and you understand, and now introduce a new data language while keeping that constant.
It sounds like A/B testing, right? You have like your control version of how things used to go, and then you change one thing, see how it works, if it's better or not, if it's actually to your liking. And when you mention about the startups, I guess that's usually like the most common, I guess, mistake. They want to do things very, very fast, like you mentioned, new languages, everything. But the thing is that maybe those things or ideas, they tend to not even connect together, right? Maybe it doesn't make sense even. Like if you're a startup, right? Like, does it make sense for you to actually go to the microservices or like Kubernetes if you have like 100 users? So yeah, that's actually, a very, very good point you made.
I'm a fan of, there was a blog post from a decade ago or so. The title was something like Use Boring Technologies. And it was suggesting, kind of arbitrarily suggested, that each startup has 3 innovation tokens. And you get to spend them however you want. But if you spend all 3 of them on like your infrastructure, your language, and then you're out of innovation tokens. You've spent as much as you can. And I thought that was a good reminder that you shouldn't change everything at once.
Yeah, that's true, right? Change, not everything has to change actually, and that kind of makes sense.
But which I guess goes back to what I was talking about, the brilliant design of the Python sockets module. If you don't need to change everything at once. We can just have files work like they always have in Unix. You can have sockets work like they always have in Unix, because you're changing language and you're coming into Python. A lot is changing. Let's just keep everything else familiar.
Okay, so since we're talking about things that not changed, not changed over the years, right? So what do you think, in Python that they really got it right over the years, from the start even, or maybe, later decisions? You mentioned a lot about sockets, right? Maybe there's something else that you actually liked, how it was implemented?
I first heard about Python from overhearing a grad student. There was this, there are some professors that are not as interesting, but then there's those young grad students that are kind of cool and fiery. And there was this great guy at Georgia Tech, grad student at the time, Ian Smith, I believe his name was. He taught the Lisp class, but made it really interesting and like had us all write Connect 4 players in Lisp. And then he did a tournament between them to see whose would win. And I overheard him in the hallway telling another grad student, you've got to check out this language, Python. Clearly, it was written by someone who knew programming languages. Because at least in the back in the 1990s, many programming languages were written just by amateurs who didn't actually know the previous work that had been done in programming languages. But Python was written by someone who knew a lot of previous work and was able to not make the old mistakes. And so having overheard Ian talking about it, I downloaded it, tried it out, and immediately was in love and immediately knew that this was my alternative. I'd been looking for an alternative to awk, but I was not going to use Perl. I was not going to use PHP. And now I had found where I was going to land. And the things that it did right off were like all other scripting languages, it seemed, would, if you tried to use a string as a number, well, they didn't want to cause you any trouble. And so they would just magically try to convert, making a guess about how you would want that conversion done, your string to a number. And Python just said, I'm going to raise an exception and just make you be explicit. Just put float or int around it. I thought that was brilliant, that the types were themselves callables. You just reuse an existing syntax, the function call, but it works with types instead of some separate syntax that's special only to types. So those were two brilliant things, is having a generic syntax that worked with both types and with callable routines, functions, and methods. And I loved how the data structures were composable. In other scripting languages, you either couldn't put a dictionary as a value in a dictionary, as a value in a list, or it was some abstruse syntax that then, to get values back out, required ample characters on both the left and right-hand side of the name of the data structure. In Python, you just put a list as a value in a dictionary, and it just worked. Everything was orthogonal. Everything was Lego pieces that just fit together and let you build larger data structures out of little simple ones that you could learn in a hurry. So those were the things that I really noticed first, was the data structures being simple, orthogonal, and composable.
Makes sense, yeah. And I guess one of the reasons why Python is has like more and more traction, it's just because of its ease of use. And like in some ways, it's super easy to understand compared to the other languages, and the boilerplate around them, right? With Python, it's like very, very simple. Okay, so about the changes then, from no changes to the changes. So like, I guess you heard, that they're planning to kind of remove the global interpreter lock. So any thoughts, is it good, in your, like, how do you see the change?
In general, when a change can be done safely, and for many years, it did not look like it could be done safely. Small experiments in removing the global interpreter lock would fail, derail, would find the much more complex edge cases all over the standard library than perhaps they had imagined. I am in favor of things special. So I actually don't like it much when Python changes, because it often just makes Python more complex. It means that there's more for beginners to have to learn. It just keeps getting more complicated. But I do like changes that bring Python's behavior into line with what people natively expect. For example, the brilliant work that was done that wound up in dictionaries remembering their order. Resolved what must have been at least dozens of Stack Overflow questions of people saying, I just built this dictionary and then I iterated over it and it came out in a different order. Now, you can say over and over again, hash tables don't remember their order. And that simply isn't the expectation that naive programmers bring. If you explain it 1,000 times, when the next new programmer arrives, you have to explain it for 1,001st. Experienced programmers, unfortunately, will often interiorize, there's a better word for internalize, a limitation until they think it's just natural and normal. And no, it's a good thing that dictionaries don't keep their order. But you can tell by the novice's questions, especially if you've done any teaching, where a programming language and its features is at odds from just natural human expectations. That a dictionary should keep its order is just a natural human expectation. And I'm so happy that Python now matches that expectation. That's a major source of friction that's now gone. Similarly, the expectation that if you start a thread, it should start running and executing code is a pretty natural expectation. The fact that threads should be able to make progress at the same time, the fact that if multiple threads are doing multiple math routines, they should all run on multiple CPUs is a very natural expectation. And you're simply creating a permanent you're creating permanent load on the language and its users when that has to be explained over and over again that no, there's a global interpreter lock. No, it's I/O that will really let you free to run another thread. And so I remember, and I'm happy to see that this has arrived as well, I remember advocating several PyCons ago for, can we at least run multiple interpreters? And it may be, maybe they can't share much, but you could at least then use Python to have multiple workers sharing a same message queue or database. And it looks like finally multiple interpreters have come along, and that a removal of the global interpreter lock will be possible, because again, it's simply an expense for users, developers learning the language, when sort of an obvious behavior winds up running smack into an unexpected constraint that has to be explained and documented over and over again.
So basically, if it's not explicitly defined, everyone will ask questions about it, like in general, right? Or they will find hacks, how to overgo it in one or the other way. Okay. So coming to the end, and like waiting for tomorrow, so I wanted to actually pick your brain about things, how you're, prepping for your keynotes. You mentioned that when some idea comes to you, right, you start to write it, iterate over how it feels and whatnot. So any tips actually for like how to figure out how does it work for you, just to start doing it, or like basically any tips or tips preparing for your, like, I don't know, presentation, or like even considering, doing a CFP or some talk?
So a CFP is a very specific situation, because there you have to know what you're going to say ahead of time. And you have to convince a programming committee that you will make good use of a slot that someone else could talk in instead. A slot that's one of a limited number of slots at that conference and that really needs to bring value. And so you need to, months ahead of time, know your idea, know what conclusion it will have, and write all of that up, not knowing if it will be accepted or not. So I find that if I decide to submit to a CFP, it's because I have a really specific idea that I'm sure is a good one, where I know where it's going to go, and can explain all of that ahead of time. With a talk like the one I'm doing tomorrow, often invitations arrive in a year when maybe I don't apply to any CFPs, because at the moment I've said most of the obvious, predictable things that I can think of to say. Or I look out into the world of other speakers and I see the things I would be saying already being clearly spoken by new or experienced speakers at Python conferences. And I say, oh, the job is done. I can just enjoy PyCon this year. Everything that needs explaining looks like it's going to get explained. But then an invitation comes, an opportunity to speak to the community, and I kind of dig in and think, well, if I were going to get up in front of people, what would I say next? And I have in a little private repository where I write my talks, I have a file called my dark materials. There's an old quote in Milton where as Satan stands on the edge of chaos, looking outside of the created world at all the materials from which new worlds could be made. It says he stand and he looked at the sort of God's dark materials that might someday make new worlds. So I have a file called my dark materials where when I write talks, I never fit in everything I want to say. And so I don't dispose of those ideas or those slides. I just cut and paste them, or cut them, and paste them into this dark materials file so that they're around later when I get an invitation and need something to talk about. And so I look through dark materials, and very often, all right, I'm going to reveal a secret here right at the end. If you look back at my last few talks, the core of, I think, my last several talks has been whatever code I wrote a few weeks before the invitation to speak came in. Not to give anything away, but my talk tomorrow will have at its core a coding example that was a little function that I needed to write in order to graph the humidity and temperature in my house. I had just written that piece of code when the invitation came in, and as I looked over the dark materials file and thought about the code, I realized that I maybe could illustrate some big ideas I'd been thinking about how we structure Python code using this simple routine to kind of show how our code relates to data structures, how subroutines relate to our main routines. And very often I use some little recent Python script I've written as kind of a kernel or seed or core idea that I can then use to make general points about how we write code.
That's a good tip. I'm going to steal that. So I hope, the listeners are going to use that as well. And one last question, do you still get nervous? You gave like tons of talks, do you have any, rituals, to calm down the nervousness, or?
The, having the early talk slot in the day, can help you wake up and are just, racing to get everything ready and to get to the site. You don't have much time to think. In this case, it will be a late afternoon tutorial. I think that it's just with practice. I've learned that if I just make an entertaining story out of what I'm saying, then whether people find it novel or not, whether they find it immediately applicable or not, I at least can kind of try to make it a rousing story that carries the emotions along. I try to put in little opinions, bits of feeling of highs and lows as I was working on a little project. A final thing that I do is I try, for instance, by writing this little piece of code on the screen, I'll show how I loop over some data structures, how I combine some data, and how I used Plotly for the first time to put it on the screen. If there are programmers in the audience for whom my big ideas about software architecture don't land, because it totally doesn't apply to their situation, or it's just in ways I don't realize wrong for their situation, or they're a new coder and it just, all this stuff I talk about doesn't make sense, maybe they'll know Plotly exists by the end of the talk. Maybe they'll see that it can be quickly be used to draw some lines on the screen. They'll see how I write code. I'm going to show when I write a little subroutine that I write the middle idea first and then work my way out. So I try to, fractal might be too big a word for what I do, but I try to include some little gems at every level of detail, from how I write a Python script to little tools that I use, all the way up to my big ideas, so that wherever a listener is at, they hopefully take something away from the talk, whether the big ideas I'm proud of wind up helping them or not.
Oh, now I'm even more excited, to learn all of these things. Like, it's very interesting, to compare, how you think, how others, putting things into perspective, doing their projects and whatnot. So I guess that's going to be a very, very fun ending of a day, hearing your keynote. So thank you, Brandon. It was very, very nice to hear, your journey, how you got into astronomy, and basically, your creation of the open source, or like wrapping at start, right? The PyEphem and then the Skyfield, and actually to hear your input, why pandas from the ground up came, and how did you end up with the Python network programming. So it was very, very nice to hear from you, and thank you for this nice talk, and good luck in your tomorrow's keynote.
Thank you for having me. It's instead of sitting in the lobby of the hotel waiting for Python programmers to wander down, this has been a great way to get started with being part of the conference, with interacting, with starting to tell stories. So thank you very much for having me.